Morning, everybody. The video playing on the screen right now is trying to explain how to turn in your quiz sheets. So key things that you need to do is you need to staple them all together. However many you have, just staple them together. Yes?
I forgot.
No, it's okay. It's okay. It's okay. It's okay. Staple them together. Get your name on the front and get the total number of points from all your quizzes on the front page. So not per page, but like all your points on the quizzes on the front page, okay? Staple together, name on the front, total amount of points. I will accept these quiz sheets anytime until next Friday. So let's just say the fourth exam in here, right? You can turn in your quizzes until the day of the last exam, okay? That exam is not during finals week. I don't take anything during finals week. No quiz sheets, no corrections to your grade, nothing. The only grade that you get assigned during finals week is your exam autopsy grade. We'll talk about that a little bit later. So really important that you get these to me sometime within the next couple of weeks and before our fourth exam. That goes also for any corrections to your grade that need to be made. Like if I've missed putting in a lab score, or more commonly, the difference between a 10 and a 0 when I'm entering it into Canvas is me missing the number 1, right? Okay, on the keyboard. So sometimes, people email, Mr. Bailey, you gave me a 0, but I was there. It's a typo. It was supposed to be 10. So just make sure you've got all your lab scores that you deserve. Check your homework scores. Sometimes Wiley Plus messes up in sending an individual score over. I've been kind of checking the whole semester, and I haven't seen any problems, but there's too many of you for me to check everybody individually. So just, again, make sure that as we move here into this very last bit of class, that your grade is correct as it should be. Both homework, labs, and I need to know any corrections that need to be done right away, because I will not correct anything during finals week other than your exam autopsy. So yeah, don't panic if you don't have your quizzes here today. You can get these to me next Monday, Tuesday, right? It's okay. All right, so that's the quizzes. I'll bring that back up maybe towards the end so that people can see it again. We were talking about nuclear stability. I don't have a place to turn them in yet. We'll get there. I'll kick them at the end. We were talking about nuclear stability, and I'm going to try and delve in a little bit into the strong force here, and then we're going to talk about the different kinds of radioactivity. We're going to talk about half-life and then move into how we measure radiation and how much is bad for you. All right, so I introduced you the strong nuclear force last time. And the strong nuclear force, key features, very short-ranged, acts between anything that's in the nucleus. So neutron, proton, it doesn't matter. It doesn't have to have charge. The strong force will act on it. It's named the strong force because it's stronger than the electromagnetic repulsion between atoms. But another thing that's kind of strange about nuclei, and this chart is trying to kind of show it, is that in order to be stable, it turns out that you need more neutrons than kind of one would expect. And so the straight line there represents like a 1-to-1, the atomic number being the number of protons, right? And then the number of neutrons. Kind of base assumption is that if you have too many neutrons, your atom might get too fluffy, and that means the strong force won't be able to act on far sides of the nucleus, and so it might become unstable. But that's not what's true. All those dots right there represent stable elements. And basically, kind of a little rule of thumb is anything after atomic number 20, before then, 1-to-1 gives you stability. For example, carbon 12. Got 12 neutrons, 12 protons. Totally stable. But carbon-14 is unstable, has 2 excess neutrons, and that gives it some instability and therefore some radioactivity. So before atomic number 20, it's essentially 1-to-1. After that, you actually need more neutrons in your nucleus than protons in order to be stable. The strong force gets its energy or its ability to kind of hold nuclei together by pulling a little bit of an Einstein and doing some E equals mc squared business. It turns out that the mass of a neutron and the mass of a proton, when they're bound inside of a nucleus, is different than if you saw that neutron or proton all by itself. This, it's called the mass defect or the mass difference. This kind of change in mass, one would think like a proton's a proton no matter where it is. But the actual masses of protons and neutrons change depending on what nucleus they happen to be in. They're heavier when they're free, but when they come together, they lose some of their mass. And the question is, where does the mass go? And the answer is, it goes into the strong force. It goes into the energy required to keep the nucleus together. Let's see, we did I did it over here, yeah, right? So I kind of showed you how we use these funny mass units in nuclear physics because, I mean, there's just so little mass going on here. And I also warned you that you really want to give all of the significant digits you are given in a problem. You want to make sure you use all of them. To calculate like the binding energy, you have to figure out what the missing mass is and then convert that into an energy unit. But we can calculate this thing called the mass defect if we come back here and we use this. Let's see. I know you can't see what I'm doing. Let's copy that and bring it back over here to the binding energy. So that's a conversion factor between two different kinds of masses. The mass defect, okay, that's basically the binding energy converted into a mass unit, okay? And because you have this, right, we can get from an energy, right, as long as we have the speed of light squared, we can get back to a mass. I think you have a homework problem where you're asked to calculate the mass defect, okay? And so all you need to do is use this conversion factor to figure out what the binding energy is. If they tell you the binding energy, convert it into the mass defect by using the thing that's in my box right here, okay? Or vice versa. The point is, when a nucleus stitches itself together for any reason, it has to get some glue from somewhere. And the place it gets its glue from is the mass of the individual neutrons and protons in that nucleus. Some of that mass gets converted into an energy that holds the nucleus together. This is a plot we're going to come back to. Sometimes this plot's drawn like this, other times it's drawn upside down. It actually doesn't matter which way you draw it. The point is that there is a curve here, okay? And you can kind of see that curve if you follow the dots. What this is doing is it's trying to give an indication for how much binding energy there is in different atoms. So the binding energy per nucleon. Nucleon means proton or neutron, okay? And then your mass number, which is the total number of protons and neutrons in the nucleus. As we follow this curve, like hydrogen has a pretty low binding energy per proton and neutron. Of course, hydrogen only has what in its nucleus? It's just a proton, right? It's the simplest of all atoms. It's a proton in the nucleus with one electron. in its associated orbitals. But as we continue to add, as we add atomic mass, right, the binding energy comes up and peaks and then begins to come back down again, okay? And it peaks here right around iron and nickel. Iron and nickel have the highest binding energy of all the elements that we have on the periodic table. And what that means is that they are the most stable. They're the ones that are hardest to kind of split or get the nucleus to give up any of its energy. Because the binding energy is so high for iron and nickel, it just really kind of holds on to that nucleus and doesn't let anything happen. And so that's why iron and nickel tend to be among some of the most stable when it comes to radioactivity. And as we'll see later, they are a dead end for every process involved in creating nuclei, and we create nuclei by doing fusion. But I'm getting a little bit ahead of myself, but we'll get back to that. The point is, the strong force comes from converting the masses of protons and neutrons into energy. And that energy is used to hold the nucleus together. That energy is not equal among the elements. And the closer you get to iron and nickel on the periodic table, the more energy is being used to glue that thing together. All right, back to Marie and Pierre Curie. There's Marie. This is taken, I believe, like circa 1910. Pierre's already been killed in his accident. She continues her work on isolating things. Now, Marie and Pierre and Henri Becquerel kind of started all working together trying to isolate not just the elements that were producing radioactivity, but then also classifying the different kinds of radioactivity that they were measuring. And in so doing, they discovered that there were 3 types of radioactivity. Now, physicists being kind of an uncreative lot, they just kind of went ABC, but then realized that sounds a little bit too easy, so it became alpha, beta, gamma, right? Just if you need to make it more complicated, just go Greek, right? So alpha radiation, beta radiation, gamma radiation. And they knew that these were 3 different types of radiation based on how they reacted with magnetic fields. So here, we got to dust off a little bit of our second unit materials, right? And don't worry, it's not going to be as traumatic as it was back then. But one of the things that we learned about charges is that they get pushed around by magnetic fields. A charge moving through a magnetic field will take an arcing or circulating path. And so as they isolated different radioactive substances, they noticed that coming out of all the substances, there was a kind of radiation that as it passed through a magnetic field, it bent, say, to the left. And then there was another type of radiation that bent to the right. So what do you conclude right away if you've got something in a magnetic field, one goes left, one goes right? They're opposite charges, right? Okay. And then, of course, if you know the direction of your magnetic field and the direction that the charge is bending, you know its sign. Turned out that alpha particles were positively charged particles, and the beta particle was a negatively charged particle. The gamma ray didn't bend at all. It shot straight through the magnetic field like it wasn't even there. So what's the charge on a gamma ray? It's neutral, okay? It's neither positive nor negative. So that was kind of the 3 primary sort of differences they noticed right away. Others would start to characterize these different types of radioactivity. And it was discovered that the alpha particle was a helium nucleus. It was 2 protons and 2 neutrons all stitched together, moving by itself. So by far and away the heaviest of all the radioactive particles. Further research would show that beta particles were electrons. That's it. They're just an electron. Really energetic one, but electrons nonetheless. And then finally, the gamma ray, it was a photon. It was pure energy. It had no mass. So alpha particle had the mass of a helium nucleus. The beta particle had the mass of an electron, and was an electron. And then the gamma ray, pure energy, pure photon, no mass whatsoever, and completely neutral. These different types of radiation have different abilities to pass through materials. And so when it comes to exposure, it's pretty important to understand like kind of which one can penetrate the most material. Well, alpha, beta, gamma, A, B, C, they are in order of their ability to get through things. Now, please don't confuse this with like safety, right? I'm safe from alpha particles just because they can't get through a piece of paper. We'll talk about safety later. But an alpha particle being the mass that it is and having the energy that it does when it comes out of a nucleus tends to get basically fouled up with, all it needs is basically, 2 electrons, okay? And then it becomes neutral helium and can go into party balloons and make kids and adults happy, right? But it can also get stopped by a piece of paper. It's energetic, and yes, you don't want to have an alpha emitter in you or around you, but like, it's nothing like gamma, right? So alpha can be stopped by a piece of paper. Beta can be stopped by a couple layers of clothing. And then gamma, you need a lot of stuff to stop a gamma ray. Gamma ray is going to get you no matter what. And it requires several inches of lead in order to really have a chance to stop a gamma ray particle. Okay, so I used to give this as a quiz question, and I stopped because people were starting to get angry. But I'm going to let you guys kind of think about it and talk to each other about this real briefly. So let's say that I bake you 3 radioactive cookies. Okay? Everybody in this room is going to get 3 radioactive cookies. One of those cookies has an alpha emitter in it, a substance that's giving off alpha particles. Another cookie is giving off beta, and your third cookie is giving off gamma. I'll let you decide if they're chocolate or chocolate chip or whatever. Okay, that's up to you. What I want you to do, discuss with your neighbor how you would minimize your exposure to radiation if I told you that you can hold one cookie in your hand, put one cookie in your pocket, and be forced to eat the third cookie. So just kind of talk about where would you put the alpha, where would you put the beta, where would you put the gamma if your only choices were eat it, pocket it, or hold it in your hand. Go. All right, have you figured out? Where are you going to put the alpha cookie?
In my hand.
In your hand? Why?
Because I don't want to ingest it.
Well, because skin can stop it. If paper can stop a alpha ray, then skin definitely can. Okay, because skin's thicker than paper. Okay, so yeah, you're going to hold on to the alpha cookie. What are you going to do with the beta cookie? Put it in your pocket? Why your pocket? Couple layers of clothing can stop a beta particle. So that leaves the gamma cookie. And you're out of choices now, right? So what do you do with the gamma cookie? You eat it. Why do you eat it? Because inside or outside, it's going to get you. There's no stopping a gamma ray. Not unless you are made of 4 to 6 inches of lead, right? So, yeah, just, again, students would always get upset, right, that they had to eat a gamma cookie. So, no quiz points attached to that one. Okay, where are these particles, where is this radiation coming from, right? Like, what is going on in a nucleus that would convince it to give up a helium nucleus? Like, why would a nucleus kick out 2 protons and 2 neutrons? More disturbingly, what the heck is an electron doing coming out of a nucleus? Like, are electrons supposed to be inside the nucleus of an atom?
No.
No. And yet, beta particles coming out of the nucleus, that's what they are. They're electrons. And then gamma rays. How are photons coming out of the nucleus? So physicists went to work trying to come to grips with figuring this out. And what was developed was a type of quantum mechanics, but for neutrons and protons. We're not going to get into the nitty-gritty details of it. Instead, we're going to talk about like sort of the after effects. What are the processes that are taking place inside of a nucleus in order to get it to emit this kind of radiation? The short version of the story, though, is that we really don't know, right, what convinces the nucleus to give up an alpha particle versus a beta particle versus a gamma ray. What we do know is that a fourth force was discovered when we started asking questions like, what the heck is going on here? That fourth force turned out to be weaker than the strong force. It was responsible for the radiation, for creating radioactive particles. It mediated or dictated or controlled when a nucleus would give up a certain kind of radiation. And because it was weaker than the strong force, what name did we pick for it? The weak nuclear force. Okay? Weak nuclear force is pretty complicated, but in the end, it is the fourth of the 4 fundamental forces that make up reality as you and I know it. Weak, strong, electromagnetic, and then gravity with its little asterisks on there that gravity isn't necessarily a force. It could also be ripples in space-time, but nobody wants to listen to that anymore. So physicists, we go back and forth. We say, yeah, gravity did it, or we say, space-time did it. It just kind of depends on the application. So, all right, but what are these processes? Okay, there's alpha, beta, and gamma. So let's start with alpha. Okay, in nuclear physics, you have this notation, right, where you have the element, and then you put the mass number up high, and you put the atomic number down low. And if you subtract these 2 numbers, what do you get? You get the number of neutrons in that element. Okay, so for alpha decay, let's not use green. Let's use black. Okay, for alpha decay, so there's a pattern here, and I'm going to use like generic symbols. I'm not going to use. We'll do actual example here in a second. But basically, what's going on in alpha decay is you have an element X. Okay. And it has a mass number A. I'm sorry that mass number uses the symbol A, because you would think atomic number would use the symbol A. It doesn't. The atomic number is the symbol Z. I didn't make the rules. Okay, I'm sorry. It's just the way it is. Okay. So what this nucleus is going to do is it's going to undergo a radioactive decay. This nucleus is unstable for many reasons. Maybe it's too big and the strong force can't hold it together. Something's happening to cause this nucleus to be unstable. And so to become stable, the weak nuclear force helps the nucleus figure out that an alpha particle has to come out. So the symbol that we use for that alpha particle, we just use helium as the symbol, right? Because that's what it is. It's a helium nucleus. Helium has an atomic number of 2 and a mass number of 4. So that helium-4 right there is the alpha particle. Okay, Those of you who've taken chemistry know that when you have sort of a chemical equation like this, where there's like an arrow telling you what to do, you have to conserve the numbers on either side, right? Like when you're balancing chemical equations, you have to have the same number of molecules or elements, whatever the reaction's going on, right? Here in nuclear physics, we do the same thing. Mass number and atomic number need to be conserved. So if the parent started with Z for its atomic number, and the helium nucleus has 2 of those protons in it, what does the remaining element, how many, I'm not saying this very well, right? What happens if you subtract 2 protons from a nucleus? What happens to its atomic number? It goes down by 2, right? So we're going to end up with a new element, Y, that is going to have 2 less protons in it. And then what's going to happen to its atomic mass number? Remember, atomic mass number is the total number of protons and neutrons. There's 4. So what's the number that goes here? Yeah, it's A minus 4. Okay. So what this is right here is it's like a template or a prototype for what's going on in a alpha decay. In alpha decay, the atomic number goes down by 2. The mass goes down by 4. If you change the atomic number of an element, what else changes? The element itself, right? Because if you mess with the number of protons, then you've changed the element. And what this is called is the transmutation of the elements. In other words, all the things that those alchemists and everything were trying to accomplish, we just did it. Let's get the periodic table back up here, okay? So here's our periodic table. If, for example, we want to turn lead into gold. That's what the alchemists always wanted to do, right? Well, there's lead, number 82. Here's gold, number 79. What do we need to do with the number of protons? We got to go down, right? So if lead somehow can be convinced to undergo alpha decay, we get to mercury, right? If we got to mercury, we can go 2 more. Ooh, we get to platinum. Let's stop there, right? Instead of gold, we'll just go straight to platinum and be done. But no, we want to get to gold. So alpha decay lets us drop the number of protons by 2. I'm not saying we can do this. We've done it. It just takes so much energy to get this to happen that you might as well just go dig the gold out of the ground anyway. So, all right. So we can go down, right? Alpha decay lets us go down, but we have to go down by 2s, right? We can't go down by 1. So let's see if we can do our lead into gold a different way, right? Let's take a look at, let's do an example of alpha decay here, right? So radium, okay, undergoes alpha decay. Here's the alpha particle, okay? And notice that the mass number dropped by 4 and the atomic number dropped by 2. This is radon. Radon on the periodic table, was it radium or radon? Radium. Just can't read my symbols. Radium, right there, okay? And if radium with 88 undergoing alpha decay, right, will lose 2 of those and end up as 86, which is radon right there. Radon gas in somebody's home is actually bad news because it means that radium has been around and radon itself is also unstable. What's one of the rules of stability? Do you remember? Anything bigger than atomic number 82? And you are automatically unstable. You are naturally unstable. Anything above 82 is going to undergo alpha, beta, and gamma in a quest to get down to 82 or lower. Okay? So radon gas is radioactive. It sits in your house if you have a basement, and emits alpha particles, and that can be really bad for your health. So if an alpha particle can't get through your skin, how can an alpha particle be bad for your health? What do your lungs do? They exchange material, gas, between the inside of you and the outside of you. The lungs' job isn't to keep you alive. The lungs' job is to take in gas, whatever gas is available, and put it into your bloodstream. If that gas happens to have oxygen in it, yay, you stay alive, right? But if it doesn't, your lungs will continue to exchange gas. So if you breathe in radon gas, what is your lungs going to do with radon gas? It's going to put it into your bloodstream. And now you have an alpha emitter in your bloodstream. What's cancer of the blood called? Leukemia. Leukemia rates are higher in the Midwest. Okay? Not because they're from the Midwest, but because the Midwest does have a lot of tornadoes, and in order to escape a tornado, where do you build the shelter? Underground, in the basement. The ground is naturally radioactive. The ground's a fantastic source of radon gas. Here in Fresno, I think we have, like 3 houses that have basements in it, right? Because you can't dig through the hard pan here in the Central Valley. So, like, they tried, and they had to use dynamite, basically, to to dig through the hard pan, right? So we just don't have basements here. We don't worry about it because the radon's a pretty heavy gas. It'll stay, like, in the ground, in the dirt. You go digging in your backyard, never be exposed to radon, right? But a basement is a place where that gas can collect, being the heaviest gas around, and it'll collect in the basement. And so there are radon test kits. There's a government agency that's responsible for testing people's homes. If you think that you have radon, you want to. So here on the West Coast, we have fire alarms and like earthquake alert kinds of things. In the Midwest, they have fire alarms and radon detectors in their basements. Yeah. One of the things you're going to learn after today's lecture is that the universe is out to get you in many different ways. But it's okay. We'll make it all right in the end, and I'll help you contextualize just what the heck is going on. What's this? Speak of the devil. It's a smoke detector. Okay. If you open up your smoke detector, you're going to see this label. Okay. See how this label says radioactive on it? Okay. It even tells you what the radioactive material is. Americium-241. Okay. That on the periodic table sits right here, atomic number 95. And why are they putting radioactive elements in our smoke detectors? I thought smoke detectors were supposed to save our lives, not shorten them. How does a smoke detector know when smoke has been there? Inside of this detector, there's a source of alpha particles, and those alpha particles come streaming out and they hit a detector. If smoke enters the device, what happens to the alpha particles when they hit a smoke particle? They get stopped, right? Remember? Alpha particles can get stopped by a piece of paper. They can definitely get stopped by a smoke particle. Okay? And so the alpha particle will get absorbed, which means fewer alpha particles will hit the detector. And when the detector detects that drop in flux from the alpha particles, it goes off. Makes that really bad noise in the middle of the night. You have to go hit the test button. That's a false alarm.
I opened a smoke detector recently. I don't know if it's just really old, but there was an infrared light inside.
That's a different kind of detector, yes.
Okay.
They're less reliable.
Oh, okay.
Yes. So, used to be smoke detectors, you had to check the battery every 6 months or so. Now you buy a smoke detector, it's got a battery in it that lasts like 10 years. Right? Yeah, they're disposable. You should dispose of them correctly because they do have. Yeah. Now it just beeps all the time. Yeah. I didn't say that. The scientists have no say over like the government regulations for this stuff, but like, yeah. All right, so let's move on to beta decay, okay? Now this one's a little bit more confusing or like interesting. So what we have in beta decay, so here's an example of carbon-14. Carbon-14 undergoes beta decay, okay? Carbon-14, when it undergoes beta decay, will turn into nitrogen. So carbon has an atomic number of 6, and nitrogen has an atomic number of 7. Where did the proton come from? A beta decay is an electron coming sailing out of the nucleus. Okay? So the thing that's going on with beta decay, you have again, the original, the OG. What we're getting out is an electron. Okay? Now, the nuclear symbol for an electron, its mass number is 0. It has mass, but it's 1,000 times smaller than a neutron or a proton. So mass number being rounded to the nearest integer, we just give it 0 mass. Okay? And then it has a charge of -1. Again, we have to balance the mass number and atomic number on either side of the arrow. So what would the resulting element, what would happen to its mass number? Doesn't change at all, right? It's just A, okay? But what happens to its atomic number? We have to add 1 to it. That's not the end of the story, by the way. It turns out that there is another particle that comes out called a neutrino. More on that in a bit. An electron is kicked out of the nucleus where it had no business being there in the first place. And the nucleus suddenly goes from having 6 protons to having 7 protons without ever changing the total number of neutrons and protons. That's the clue. What's going on here? If a neutron can get rid of negative charge, remember a neutron is neutral, doesn't mean it has 0, it means it has what? An equal number of positive and negatives, right? So if it can get rid of the negative charge, and what's a negative charge going somewhere? What do we call that? An electron, right? Okay. What's left behind? Something with the mass of a neutron but with positive charge, otherwise known as a proton. So under beta decay, what we think is going on is a neutron becomes a proton plus an electron, and that electron gets kicked out at very high speed, very high energy, much higher energy than the alpha particle. In order for everything to work out, conservation of energy, conservation of mass, everything else, a new particle is required called the neutrino. Neutrino is a word, Italian, I think, that means a little massless one. And it turns out that neutrinos actually do have mass. It's very, very tiny, but it's an important amount of mass for reasons we may get into later if we talk about particle physics. But it's enough to know that you get an electron coming out, and the atomic number does what? Goes up or down? Up. So let's turn lead into gold. For lead, we do 2 alpha decays, right? We go down by 2 atomic numbers. So there's 1 alpha decay, there's the next alpha decay, and then to get to gold, beta. Because beta will move you up by 1, and alpha will move you down by 2. Again, this requires a whole lot more energy than the amount of gold you get out. The gold you end up with is radioactive itself, so not great for using in legal tender, right? But it is technically possible. It's just not practical at all. You might notice up here that there's kind of two different kinds of beta decay that are happening. Okay, so in one of them, an electron comes out. Okay, we usually just call this beta decay. And then in another version of beta decay, which we call positron decay, instead of a electron coming out, a positron comes out. A positron is an electron, it just has positive charge. It's got the same mass, all that good stuff. It's positively charged instead of negatively charged. And you'll notice here that we kind of, in positron decay, we reverse the rules for beta decay. I'm not so concerned about you knowing the differences here, being able to do both. We'll focus on normal, everyday beta decay because it is the most common. But you will see situations online, other textbooks, where they start talking about positron decay. Just realize it's beta decay, but the positive version of it. Technically, in beta decay, it's the anti-neutrino that comes out. When I drew mine, I drew a bar over the top. That means the anti-version. And in particle physics, anti means opposite charge. So what is an anti-electron? It's not a proton, it's a positron. Okay? We just have a special name for an anti-electron. Everything else, like the anti-neutrino, is the opposite charge of a standard neutrino. Okay? Same thing, opposite. So what's anti-hydrogen? It's hydrogen with opposite charges being made of it. It's literally antimatter. Antimatter is the same thing but with opposite charges on it. So an antiproton in the nucleus, which would be a negatively charged proton, right? So we call it the antiproton, and then around that antiproton would be a positron. That's what antihydrogen would be. But that's getting too far into particle physics. All right, let's do gamma. Gamma's a lot easier. Gamma, nothing happens, okay? The gamma photon has no charge and it has no mass. And so what you end up with is the same thing. It's just that typically what goes on is that you have, and it's indicated by this little asterisk right here. That asterisk on the OG element means that the element was in some sort of excited state. Its nucleus was in an excited state. Much the same way that an atom can have electrons in an excited state and they come crashing back down, the nucleus can be in a similar idea. The neutrons and protons in the nucleus can have excess energy and be in excited quantum states. And when they revert back to their ground states, they'll kick out a gamma ray photon and become more stable. I think, I've got an example here, right? So in this example, we're starting with boron, okay? Boron can undergo a type of so it can do two different beta decays, right? In one of those, it just ends up beta decaying and becoming carbon. But in another version, it comes down, makes carbon-12, but that carbon-12 ends up in an excited state in its nucleus, and so it has to undergo another gamma decay in order to get down to the more stable version of it. So the weak force is what determines whether or not any of that is taking place. The way we measure radioactivity is through a concept called half-life. What I'm going to do right now is I'm going to pass out some dice. Okay, I'm going to just put containers. Start passing these. Oh, hold on a second. We need to count. Okay, I need 34 volunteers. Okay, so everybody's volunteering. Okay, and I need everybody to take, let's do 4 die. Okay, so you should end up with 4 dice, right, when you're all done. So everybody take 4. It doesn't matter I know it matters, but it doesn't matter what color you get. Okay, just take 4 and pass it on. Okay, you're not allowed to keep these, right? Okay, 1 right there. Okay, just hand those down. Please try not to play with them until I tell you. You're going to be able to roll them plenty, don't worry. Okay. And then also I need you to take 4 pieces of paper. Take 4 of these scrap pieces of paper, and I'll come by and pick up the excess. So you should have 4 die, and you should have 4 pieces of paper by the time you're all done. Okay, half-life. What is half-life? Well, yesterday we celebrated the 25th anniversary of one of the greatest video games of all time. Okay, it was called Half-Life. If you ever get a chance to play Half-Life or Half-Life 2, I realize for some of you this video game's older than you are, but it changed video games forever. Before Half-Life, first-person shooters they were boring. Okay, after Half-Life, they were incredible. It's an experience to have, and I highly recommend it. It often is offered for free on Steam, so shouldn't cost very much to get it. The protagonist in the Half-Life video game is Gordon Freeman. He has a PhD in physics. It has absolutely no purpose beyond the introduction of the game, but there you go, right? Physicists can be heroes. He carries a crowbar. Watch out. Actual Half-Life, the scientific version of Half-Life, is a little bit more complicated. And the reason that I've passed out dice and pieces of paper is because I want to run a simulation. I want to show you what Half-Life is. Extra papers? I'm going to show you what Half-Life is so that you can get a sense that radioactivity is governed by randomness. Whether a nucleus gives off a radioactive particle or not is totally random. There's no way to predict when or if an unstable nucleus is going to do anything about its instability. Half-life is an attempt to characterize how likely an atom is going to do something, and we are going to measure that half-life. The reason you have 4 die and 4 pieces of paper is that you are going to represent 4 individual nuclei of an unstable element that we are going to call, for lack of a better word, polonium. Okay? Polonium is radioactive, and each nucleus has a random chance of decaying. You have 6-sided dice. What is the chance of you rolling a 1? If you roll that die, what's your chance of getting a 1? It's 1 in 6. Okay? So, you have a 1 in 6 chance for an individual nucleus to undergo a decay. When a nucleus decays, what does it do? It emits a particle, doesn't it? Take your 4 pieces of paper and individually crunch them up into a ball. You should end up with 4 balls of paper and 4 die. What we are going to do together is don't do it yet, but I'm going to instruct you to take all 4 of your die, right? You're going to shake them up and you're going to roll them, okay? Any die that ends up with a 1 on its top face, you will move that die out of the pool. You will not be rolling it anymore. and you will take its corresponding piece of paper and you will throw it towards the front of the room, where I will count the number of radioactive particles per time unit that are coming out of our radioactive material. Okay, there are rules associated with this exercise. Okay? Listen very carefully. These are the rules. Number 1, you are not allowed to hit me. If you hit me, you get an F. Okay? Rule number 2, if you're in the front 2 rows, duck. Rule number 3, if you hit me, you get an F. Are we clear on the rules? Okay. Now, I am the Geiger counter, right? So I'm going to be counting these particles as they come towards the front of the room. Your aim point is here between the screens, okay? Right? Please try to throw them not all at once. If you get 2 die that end up as 1 simultaneously, get them out, push them off to the side, and then throw papers one after the other. Don't take 2 and just throw them both, okay? If you see somebody near you that's throwing their paper, just kind of wait half a second before you throw yours, right? I kind of want like a staggered stream of stuff going by so I can accurately count the number of radioactive particles that are coming through, okay? So, is everybody clear about what's going to happen? Okay. You need 4 die. Whoops. Sorry. All right, I said there were 35 or something like that. So we're going to do some really quick mental math. So let's see. What's 30 times 4? 120? Is that right? Yeah. Okay. So let's say that there's 120 die out there. What we're going to do is we're going to plot. We're going to have time on one axis, and we're going to have number of nuclei remaining on the other. And we got to go 120. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. So we're going to start with 120 nuclei, and we are going to keep track of how many nuclei we have remaining per time interval. Pick up your die. Get ready. Shake them up, roll them, remove the ones, and start throwing pieces of paper.
If I get 2 ones, do I throw 2?
Don't go again. Don't go again. How many of you threw ones that were again? Okay, so I counted about 27. So obviously we're going to be a little bit off, right? Okay. So what's 120 minus 27? 93? Let me get some time units down here. So let's see, we did minus 27, so we're at 93. That's 110, that's 100. So we're like somewhere right about there. Okay. All right. Pick up your remaining die. Did anybody lose 3? Anybody lose 2? Some people. Did anybody not lose any at all? Raise your hand. Yeah, okay, right? Just totally random. Roll your remaining die. Remove the ones and throw a piece of paper. Okay, I counted 22 that time. Okay, so what's 93 minus 22? 71. That's 90, 80, 71. This is 70, 80, 90, 100, 110, 60, 50, 40, 30, 20, 10. Okay, all right, do it again. Okay, that time I counted 24. So, like, what would you guess for like the number of decays per time as we go on? Realizing that we're getting fewer and fewer radioactive particles or nuclei. You'd expect that number to go down, right? But in this case, it didn't. What's 71 minus 24? 47. Okay, somewhere in here. Okay. Notice it was 27, then it was 22. That kind of makes sense. There should be less, right? But then it was 24, so we got more. Even though there were fewer. Is anybody out? Has anybody lost all 4 of their? Yeah? Okay. Does anybody still have all 4 of your die? Okay. How many of you with 3 left? 2? So you can see the distribution there, right? A vast majority have 2 and 3 left, but some people are out, right? While 1 or 2 people still have 4 nuclei going, right? So what determines whether or not a nucleus is going to give up a radioactive particle? Random chance, a roll of the die. I mean, nuclei aren't literally rolling die, right? But there's a random probability it's going to happen. However, there's a pattern that's starting to emerge. Pick them up, roll again. Those weren't intentional, I promise. Okay, I counted 11 that time. Okay, 47 minus 11, that's 36, isn't it? Do it again. So I counted 13 that time. Whoa, here we go. 36, 13, 23. Who knew that the hardest part of this would be basic math? Okay, do it again. So there's 11. What's 23 minus 11? 12. Somewhere in here. Okay. Anyway, let's talk about a couple of things. How many of you still have dice left? Raise your hand. Okay, many of you have dice left. How many only have 1? 2? 3? Anybody with 4? Okay. What I want you to do now is I want you to pick up all your remaining dice and roll it. If one comes up, move it out, pick up the next one, roll it again. Keep rolling, removing die. Count the total number of times it. Remember how many you started with and how many times you had to roll in order to get all of your dice to go away. And then you can throw a piece of paper if you want. So just keep rolling, counting the number of rolls it takes. That one bounced off the ceiling that time. All right, who's still rolling? All right, how many did you start with?
I just got 1 now.
Okay, how many did you start with?
1, and I had like 19 turns.
19 to get rid of 1.
Mine took 14
14 starting with,
with 1.
how many started with 2 or 3? How many times did it take you to get rid of them? 4, 7, 5. It's all over the place, isn't it? It's totally random when this is going to take place. And yet, we can come in here and we can draw a curve. We can fit this data and then ask the question, how long does it take to get to half of the remaining nuclei? Well, it looks like it takes about 2.2 Baloghs worth of time. The half-life of polonium is 2.2 Baloghs. The next half-life, so we start with 120, we go to 60. The next half-life would be at 30. Sure enough, we're about there at 4 Baloghs, right? So a half-life is the time it takes for half of your sample to undergo a radioactive decay. After 2 half-lives have gone by, how much do we have remaining? After the first half-life, how much do we have remaining? Half. And then after the second half-life, a quarter, not 0. You take a half of what you started with. So half of a half is a quarter. After the next half-life, it would be an eighth. After the next one, so on and so forth. Note how many particles we had flying per time interval, right? Started off with around 20, and then it went down into the teens, and then it went down into the tens. All right, we are going to change the rules. What I need you to do is I need everybody to come up and pick up 4 pieces of paper. You need your pieces of paper back. So send people up, grab bunches of pieces of paper, right? And everybody needs 4, so come get some. I'm doing stacks of 4 right here. Come up and grab them. Okay. Here's 4. Everybody needs 4. Oh. 4. There's 4 right there. Got 4. There's only 3 in that pile. There's 4 in that pile. 1, 2, 3. You got 4 right there. You got 4. Okay, did everybody get 4 back? No? All right, well, we'll make more. How many do you need?
That's weird. We're missing.
Oh, we got it? You got 4. We got extras? Okay. Did everybody get 4 back? Okay. We are going to alter the rules. Now you're going to throw a piece of paper when 1, 2, or 3 show up. So what's the probability of getting a 1, 2, or 3 on a single roll? 50%. So what I've done is I've altered the random chance, right, that the polonium is going to decay. I want you to throw your pieces of paper, of course, but keep track of how active the element is now compared to the first time, where activity is the rate at which particles are coming out. Okay? Pick up your dice, roll. If it gets a 1, 2, or 3, eliminate it, and throw your pieces of paper. Okay, you guys only rolled once, right? Oops. So I counted 47. So 47, let's do it in a different color. Let's do it in purple. 120 minus 50. 70? What's 120 minus 50? Is 70? Okay. So it's going to be right about there. Okay. When I first did this very first time at Fresno City College, it was right after the election where Al Gore lost to George Bush. And so my students demanded a recount. Roll again. You know, it's always a good idea to sit in the front. Not today. All right, so I think you guys can see what's going on, right? There was like another 30 or 40 tosses in there, right? How many more particles are we getting per time? We're getting a lot more, right? We're just getting a lot more particles per time. Our curve is going to be a lot steeper, okay? Which of these two elements, the green one or the purple one, is more radioactive? The purple. There's more decays per time, right? So which one has a longer half-life? The green. Ooh, interesting. The longer or bigger the half-life, the more time, right, to get through half of your sample, the less radioactive the element is. Here's my picture in case we didn't get a chance to do the simulation, okay? But we can fit mathematically what this curve is. And the mathematical fit is this equation right here. It's a decaying exponential. Now, this is written in terms of the number remaining, the number that you start with, and then some weird things that are going on over here, which I'll explain in a second. This equation they have on the screen isn't as useful as this one. The one I drew up here in the box is the equation when you do rate, like the actual measurement. It's nearly impossible to count number of radioactive nuclei. What you can do is measure the rate at which particles are coming out of the nucleus. That rate is the number per time, okay, that are decaying. And in SI units, this is known as the Curie. There's another one called the becquerel. They're actually kind of interchanged. The Curie CI or the becquerel BQ. A becquerel is 1 decay per second. A Curie is 3.7 times 10 to the 10 decays per second, or 3.7 times 10 to the 10 becquerels. It just, Curies are easier to work with because you end up having so many becquerels, nobody cares anymore, right? Whereas Curies, a little bit more useful unit. But that being said, what the heck is going on right here with the wavelength? No, sorry, that's not a wavelength, okay? That is called the, I forgot what it was called because I called it the wavelength. Is it the activity factor? No. Decay constant. Sure, why not? Okay. It happens to be equal to the natural log of 2 divided by the half-life. So, by the way, the natural log of 2 is 0.693. Okay. So this decay constant right here kind of gives you an idea of kind of how radioactive something is. Usually we're trying to solve this for time. And the way you solve that equation in the box for time is you take the natural log of the ratio of your rates and you divide them by your decay constant. So the one in red and the one in blue are very important equations for being able to pull off a calculation that many of you know as radiometric dating or carbon dating. What's carbon dating? It's like Tinder, but for carbon atoms? No, right? It's a way for us to determine how long something has been undergoing radioactive decay. What is one of the side effects of life?
Decay.
Living things exchange material with their environment. So what's one of the side effects of death? You start becoming the environment. You stop incorporating material from the environment into you. Living things respire, even plants, like they bring in gases, right? And give off wastes. Living things maintain the level of carbon-14 in them. But when they die, they stop incorporating carbon-14. Now, carbon-14 is always going to be decaying, constantly. But if you're always topping up the amount of carbon-14 in your body, then you are going to just have a constant amount, right? But as soon as you die, the carbon-14 in your bones will start decaying. And as time goes by, the amount of carbon-14 in your bones will, I don't know why I made it so personal, but I did, right? The amount of carbon-14 will get less and less and less. So 5,000 years from now, somebody digs up your bones, they can measure the amount of carbon-14 in your bones and do the calculation we're about to do to determine how long ago it was that you stopped exchanging material with your environment.
Could you show those equations again?
I'm about to. Okay, so let's pull this apart. Now, you can do this not just with bones. Adobe brick, okay, used by Native Americans and basically every early culture from the Indus Valley to the Americas. They would incorporate living plant matter, so like straw or sticks. It acted as a binder in the brick. And so you can carbon date when the bricks were made by assuming that the binder, the dry grass or whatever that they put in there, right, was gathered or killed right around the same time that the brick was fired, right? So you can, again, just pull samples of the living or once living material out to be able to carbon date quite a lot of things. Textiles, clays, obviously animal bones, all that kind of stuff you can do this carbon dating with. So what do we got? They're telling us several things here, right? We got a sample size. We know carbon-14 is doing it. They gave us the half-life of carbon-14. They gave us this rate right here, okay? So let's see what we got. Our rate, right, is 200 decays or becquerels per minute. Okay? That's what's in our sample, in 50 grams of sample. They also give us another rate. It's the rate of atmospheric carbon-14. So carbon-14 in the atmosphere does 15 decays per minute per gram. So this is where these problems can get a little bit confusing. The rates can have different units. Atmospheric or natural background rates are usually given as decays per time interval per gram of material. But notice our sample was just given in number of decays per minute. So what we need to do is we need to make sure that our rate units are the same thing. Before we can do any other calculations, we got to fix our rate units. So what's one way we can get one of these to be decays per minute per gram or get rid of the per gram? We could take the 200 and divide by 50. So if we take the 200 decays per minute and we divide by 50 grams, what will our unit come out to be? It'll be decays per minute per gram, which is exactly the same rate as our atmospheric or background amount, right? 200 divided by 50 is 4. Is that right? Yes. Okay. So 4 decays per minute per gram. That's the rate we have from our sample. It died a long time ago. But the rate that would be in existence for anything that's like living right now would be 15. Okay? The other way to do it is to take the 15 decays per minute per gram and multiply by 50 grams, right? To just get decays per minute for 450 grams. So either way you want to do it, just make sure that you have exactly the same units on, this unit and this unit need to be the same. Okay? All right. I promised Evan the equations. So the time is going to be equal to negative the natural log of r over r naught divided by the decay constant. And the decay constant was equal to 0.693 times, or divided by the half-life. Okay, it's kind of weird that there's like a negative sign in there and all that kind of stuff. It's okay. But this negative, what happens when you take the natural log of a number that is less than 1? Does anybody remember? Natural log of a number less than 1 is always a negative number. Okay, so that negative sign is going to cancel. Okay, I put the half-life in here in years, so my answer of time will come out in years. Okay, this half-life is 10,932 years, or we'd say approximately 11,000 years old. I ran out of time. That's my one example for this. We're going to get back to radiation and its units and like becquerels and curies and how much does it take to kill me and all that kind of stuff. We will do that on Monday in lab, which will be mostly lecture. What I need you to do before you leave is I need you to come up and pick up 4 pieces of paper and put them in the garbage. Have a fantastic rest of the day. I need the dice back as well. You're not allowed to keep those.